Welcome everyone, and thank you for being here. If you're looking to learn some basics of model serving and how to make both data scientists and software engineers happier with deploying models, you are in the right place. I am Isabel Zimmerman. I am a software engineer at Red Hat, and I also do a lot of data science work. I work in the Artificial Intelligence Center of Excellence on the AIOps team. And this team spends a lot of time looking at data science problems and how to build larger AI systems in the cloud. A few months ago, I started realizing that there was a gap between the knowledge of data scientists and software engineers when it came to how to get machine learning systems to work. Since then, I've been exploring MLOps and figuring out how to leverage both my data science and software engineering background to make machine learning processes better. Today I'll be talking about the Open Data Hub, which is one of the tools I use to make these systems more seamless. So I'm hoping by the end of today, everyone will know a little bit of the data science lifecycle, what the Open Data Hub is, why model serving is so complex, or MLOps is so complex, and everyone can walk away knowing how to deploy a model. So first we need to understand where data scientists are coming from. And you have to know the data science lifecycle. Data scientists start off with codifying their problem and defining metrics. This helps us know when we have completed the task we set out to do in order to make our stakeholders happy. From there, we'll make sure that we collect a bunch of data and clean it so it's in a usable state. This could be anything from making sure there's enough data and enough data that doesn't have missing values, to things like cleaning up text. After that, we'll go into feature engineering. And this is really manipulating the data that we already have in order to glean some sort of insight or to make things in a more usable state for our model training. This could be doing logarithmic transformations, or a number of other different feature engineering techniques. From there, we'll go into model training and tuning. And this is where people think data scientists do a lot of their work, but by the time we get to the model, most of the work has already been done. This is a lot of iteration, a lot of testing, and checking on our different metrics to make sure that our model is performing in terms of accuracy, or F1 scores, or precision, or recall, or whatever evaluation metrics we've set out in our step one. From there, we'll validate our model. We'll test it robustly with test data to make sure that it performs outside of our training data sets. And then we get to model deployment, and I'm putting a star here because this is where we'll be focusing our efforts today. Data scientists are very good at the codifying problems to model validation point. And then the monitoring and validation afterwards is handled very well by software engineers. But this is a little bit of a gray area that we hope to expose a little bit today. And finally, once the model is built and deployed, it is continuously monitored and validated to make sure that model health and performance application continue to be at the levels we expect them to be. But we're also tracking things here like data drift to make sure that the underlying data is not changing in some way that is unexpected. So what is the Open Data Hub? So at a very jargony level, it's an AI as a service platform on Red Hat's Kubernetes-based OpenShift container platform and Ceph object storage, which really just means it's a meta operator that is a platform for data scientists that integrates a lot of different open source projects into one spot. I like to think of it as kind of my one-stop shop for all the tools that I need. It integrates things like Kafka with Jupyter Hub, or Selden, Prometheus, and Grafana. So data scientists traditionally work locally with their favorite packages already installed in their environment. With the Open Data Hub, scientists are able to utilize all the tools they're already familiar with but work on the same platform, such as OpenShift or other Kubernetes distributions, as the teams that they might be collaborating with. So by migrating data scientists into the cloud, they're able to take advantage of all the benefits of a cloud-native environment. Not only are their models already closer to production, having your data scientists and software engineers on the same platform helps the models to be able to scale more quickly. They can be more easily orchestrated into flexible systems, and you can use container images to ensure reproducibility that might not be easily achieved when a data scientist creates a model locally in their custom environment. Oftentimes, you're installing packages or different underlying dependencies that are difficult to reproduce on a machine that's not your own. So putting it in a container image in the cloud allows for that reproducibility that gives you a robust model that you know is correct and not just something that exists on your local machine. So let's go through these different pieces of the Open Data Hub. And the first piece is Jupyter Hub. And Jupyter Hubs are really widely used by data scientists, and that's their appeal here is this is a platform we already know. From my data science background, I can hop onto Jupyter Hub and interact with the models via Jupyter notebooks, and I can also look at different visualizations and do all my Python coding in a cloud-native environment. Kafka is another piece of the Open Data Hub, and this is an open source distributed event streaming platform. This is something that will be streaming your data. If you are in the financial field, you could be processing payments. If you were looking at an IoT device, this would be continuously capturing and analyzing your sensors, anything from a smartwatch to a wind park or in a factory. So Kafka is able to write and read different streams of events and will continuously import, export, and store these streams and process them as they occur. After Kafka, there's also something called Selden, which is able to manage and serve and scale models on Kubernetes or OpenShift. So this is your model service. It deploys the model that data scientists have created and offers a real-time serving solution for model streaming use cases. It also has different options to monitor data drift, to give explainability to black box models, or to integrate progressive rollouts. Prometheus is a time series database that can store all the streamed information. It collects metrics as a timestamp and then a key value pair of a label. It works well for recording any purely numeric time series. And lastly, there is Grafana. And Grafana is an open source visualization and analytics software. It's used often to build dashboards to visualize large sets of data, especially when it comes to operational data. You can query your data, you can schedule different alerts, as well as explore your metrics, logs, traces, etc. So what makes model serving so hard? And it really hones in on the business value of data science. And it's the piece that highlights why data science is becoming such a big piece of, the cloud ecosystem. It's integrating all of these pieces together in a really interesting and elegant system. And model serving often gets lost in the mix because data scientists and software engineers have very different focuses. These are the two personas that have a lot at stake with the model services, your data scientists and your software engineers. And they have different agendas and they have different tools. Data scientists are hoping to build a model that performs well, but software engineers are more focused on building a system to leverage or inject the model into this larger application. And models historically live in silos, where their input, the model, and the output all exist in these Jupyter notebooks we've been talking about. And with a siloed model, it can be difficult to figure out a way to post this model into production. business value in AI and ML comes from models integrated into larger intelligent applications, not ones that are hidden away in a Jupyter notebook. And I'm going to repeat that. Business value comes from models that are integrated into larger intelligent applications, not ones that are hidden away in a Jupyter notebook. And that's where model serving shines. Model serving really closes that gap between data scientists and software engineers by giving some communication between these two pieces. So what would we look for in a model service? And everyone starts with the goal of model serving. You want an endpoint to send requests to your model that software engineers can use in their app. And realistically, that solves the original problem, but it does leave a lot of loose ends. How can you tell if the model is staying healthy? What if your end result isn't just from one model? And can you tell when your customers' preferences have changed? Businesses don't have a one-size-fits-all method for how machine learning systems are used. Maybe they have data that's streaming with Kafka. Maybe they do batch prediction. Maybe they do offline prediction. So once you figure out how your model needs to be deployed, you can figure out how to make your model server more useful. You can track model versions, publish metrics, or detect data drift. And these are all leveraging MLOps capabilities to make these models more useful. So one idea is you could do A/B testing. So this is, deploying part of your model's traffic, or deploying two models and routing some traffic to one model and some amount to another to see which one performs better. Maybe it's seeing which ad customers are more likely to be clicking. And if you see that customers are more likely to click one model or one ad than another, you can update it so you route more and more traffic until you achieve your optimal balance. Other times, maybe you found a structure with many computationally inexpensive models that give a higher accuracy than one very expensive model to run. So you would be creating a sort of ensemble of multiple models into one output. And model services have this capability to automatically orchestrate to combine these multiple outputs into one prediction. Another thing that is interesting to me as a data scientist is you could be tracking data drift. So maybe the data you saw 3 days ago looks like the blue data, but the data that you're seeing now is the red data. So your customers' preferences have fundamentally changed, and a model that's trying to predict the blue data would be performing quite poorly. And machine learning breaks really quietly, and it continues to run and it has no errors even if your accuracy was 0. So this data drift could go unnoticed. But model serving offers tools to automatically track and alert when data drift is known. So let's put all these pieces together. What steps and what concrete applications do you need to deploy a model? So we start in Jupyter Hub. Jupyter Hub is where your data scientist loads the data, builds the model, trains the model, tests the model, and finally has something that they're ready to put into production. And then they will be putting their model and storing it in some sort of storage. This could be Google Cloud, it could be an S3 or a Ceph bucket, or it could be Azure Blob Storage, or even a persistent volume within your OpenShift or Kubernetes cluster. From there, Selden will connect to that saved model in storage and deploy it as a REST or gRPC endpoint. And from here we kind of have two paths. We could have a data science path where you want to continue checking in on your model or maybe make a new deployment. And Jupyter Hub actually can connect back to your Selden endpoint to explore the model and maybe roll out a new version or make some updates or check for data drift. But of course, it's not just the data scientists. You could also have an SRE type path. And they would want to be looking at exploring the metrics that Prometheus is gathering from the model or even the overall cluster and seeing how a deployed model is affecting the cluster health as a whole. These metrics would be exported from Prometheus automatically into Grafana, where you can have beautiful dashboards to easily understand your model's health, to visualize different memory usages, CPU usages, latency, and any other metrics that you are interested in building. And of course, all of these pieces are already deployed when you implement the Open Data Hub operator. So this is a quick and easy end-to-end, just 4 applications for your entire machine learning workflow. One for making the model, for deploying the model, for collecting data, as well as visualizing the data you've collected. Let's look and see how this occurs in production. So we'll start in our OpenShift cluster. So you can see I have a really specialized data science view right now. I have Jupyter Hub and Selden primarily, and these are all the tools that I need on the data science half. We can launch directly into our Jupyter Hub notebook, and we can pretend like we're all data scientists for a moment and really look through what this process is. If we start out, let's look at something that I know exists. And we'll start with a project that is coming out of the AI Ops team right now, where we're looking to build AI systems for CI/CD processes. So we're taking these continuous integration, continuous deployments, logs, and doing some term frequency analysis and other transformations to try to find how to speed up different CI/CD processes. So we can see here that this is, first of all, just looking at the size of this scroll bar, that this is a very long and probably complex notebook. We'll go through it very quickly. We see data being loaded, we see graphs being built. This is all on GitHub if you are interested. We're looking at different models being tested. And it's a very complex and in-depth notebook with a lot going on, and you could see why this piece could be difficult to integrate. So we see here kind of our end product is that we have a term frequency that gets put into a k-means clustering model. And I did make, just for simplicity's sake, a smaller version of this notebook. We're importing all of our specialized libraries. We're loading our data set. We are training our TF-IDF vectorizer and k-means clustering pipeline. And we're combining these two text mining and machine learning models into one pipeline using sklearn. And this pipeline, that's made up of 2 models in sequence, is saved as a model.joblib, and we sanity check it locally, making sure that we get the response that is expected. And then we'll set up our S3 storage so we can store this in our cloud environment. Here you can see we've uploaded this model into our Ceph bucket, and that means we are ready for a model service. So let's hop back over to our OpenShift cluster. So if I go to the Administrator tab, I can look at the installed operators. And because this is a specialized cluster for just the data science pieces. There's different projects here that include different operators. They're all managed by the Open Data Hub, which is a meta operator. This is just, again, specialized for data scientists, which is why we don't see all of those different operators on this list. So we'll hop into the Selden deployment, and we will create a new instance from YAML. So we can see here, we just added a new bucket, so I'm going to update that name. But this deployment is quite simple. All we really have to specify is a name for the deployment itself, a name for the model inside of this deployment. We specify that it's an sklearn server, which is because we made an sklearn pipeline that is being deployed. And we give it the model URI, which is just the location that it's saved on that Ceph bucket where we just uploaded the model.joblib to. Next, we have a container secret, and this is giving all of the credentials to get into the S3 bucket that's stored in a secure fashion. We let the deployment know that it's a classifier and that it should be using a predict method on strings. And here I would click create. However, for the sake of time, I do already have this deployed, and we can check in to make sure it's still running. Yep, build log clustering sklearn. State is available. Let's hop over to our developer view. This is indeed our build log clustering sklearn model. We can see we have our default and our classifier, where our pipeline is piped into, and we're given this route that we can copy that we'll be putting into our Jupyter notebook to get results back. So we're going to ignore this. My Jupyter notebook is smarter than I am. It asks me all the time if I would like to save. And let's update our service URL to the URL that was already created. Turns out it was already updated. And then we'll build a test set. So we would like to check this model in our Jupyter notebook. We can convert the data to a JSON format so it can be correctly ingested by Selden. With a good response, we can see that we have the same results, it looks like, from our local test, which means our model service is up and running. So this is really just a very quick introduction to what the Open Data Hub provides for software engineers and data scientists. The Open Data Hub provides the framework for all of these different pieces to be integrated together seamlessly by providing all of these operators as tools for data scientists. Alright, now that we have a good idea of what that end-to-end machine learning model looks like, let's recap everything we've just gone over today. One thing I want you guys to take home with you is that as a data scientist, I should be able to spend the bulk of my time doing data science. As a software engineer, I should be able to spend the bulk of my time doing software engineering. These people don't want to give each other headaches, and we don't want to get into the habit of passing models off that are difficult to deploy. We can use tools like the Open Data Hub to simplify our end-to-end machine learning workflow, and specifically Selden Core to serve our models. Of course, this workflow is not perfect. I spent months playing in the world of YAML and building REST gateways, winning those hard-won knowledge battles. and these skills typically exist outside of your typical data scientist realm of expertise. The workflow is not perfect, but there certainly are incentives for model serving, and I hope I've been able to make those more clear today. So, do we need model serving? To help data scientists and software engineers be able to speak a little bit of the same language, it helps. And to be able to pinpoint where things go wrong, it helps. I'm hoping that this talk gave you a little bit of insight into our original questions of what is the data science lifecycle? What is the Open Data Hub? Why is model serving so complex? How can I deploy a model? And I thank you all for joining. Happy local time zone to you all. I look forward to chatting with you and answering your questions. Thank you.